Okay, let's get going for this week, where we're going to be talking about hierarchical models and estimating those with our spin arm, and more on Thursday, estimating them with DRMS. So, talking about Stan, let's talk about the fact that as an employee of Columbia, as a developer of Stan, as a user of Stan for outside interest, that creates the appearance conflict of interest that you should be aware of if you're not already aware of it. So what are hierarchical models? Hierarchical models are not a big deal. In Bayesian terms, a hierarchical model is nothing more than some sort of posterior distribution where the prior for one parameter is specified conditional on some other parameter. And so this is nothing more than an application of the general multiplication rule. So in principle, I could specify some prior on the parameters theta, conditional on other parameters phi. So if I take a marginal PDF for phi, multiply it by a conditional PDF for theta, given phi, inside that integral, I'd have a joint PDF between parameters phi and other parameters theta. And if I took the multivariate integral over that joint PDF between phi and theta, integrated it over phi, I'd be left with a prior PDF for theta alone. Indeed, this is pretty much what the Hamiltonian Monte Carlo does. It introduces all these momentum parameters and then integrates them out. You don't even see them. It doesn't integrate them out analytically. It just, with Stan, drawing from the joint distribution of the position and the momentum parameters. And usually, like always, you don't care about the momentum parameters. So Stan doesn't even bother to return them to you. So, we can't really do these integrals analytically in very many cases. But the sort of MCMC equivalent of doing one of these marginalizations of like a big distribution into a smaller distribution is just draw from the joint distribution of everything. And if you don't care about something, then don't look at it. Like if you have some utility function that depends on like this margin and that margin, but not these other margins, then just evaluate the utility function, using the things that matter. So we don't really analytically marginalize. We just draw from joint distributions, and we don't pay attention to the margins we don't care about. But the margins of everything else are correct and in general are going to be correlated with each other. So the Bayesian model, okay, we specify a prior conditional on some other unknown, and we're going to estimate the joint distribution of all the unknowns conditional on all the known data. So it's no different conceptually from what we were doing before. And indeed, we've seen actually a number of examples of these hierarchical structures before, even if we didn't sort of explicitly talk about that at the time. Now, it was in the homework from last week on police shootings. Yeah, in the appendix of the paper, they did say, okay, this is like a hierarchical model or whatever, but it was no big deal. We just had these sort of bivariate normal priors on the county level intercepts that go into the multinomial likelihood. So that was one example of hierarchical structures. The Finnish horseshoe prior that we talked about for estimating models when you have tons of predictors and you think most of them are zero, but you don't know which ones are non-zero. So that was an example of a hierarchical prior. It's a normal prior with some standard deviation. Okay, what's the prior on that standard deviation? Cauchy. What's the scale of that Cauchy? Another parameter. And then it's like 6 levels deep or something of parameters but it's just like this conditional on that, conditional on that, conditional on that, conditional on that, all multiplied together implies some joint prior for the unknowns, and the marginal distribution of the prior on that coefficient in the finished horseshoe had properties that people think are good for, you know, priors in a situation where you have lots of predictors, but you think most of them probably don't matter very much. It had a high concentration at 0, but extraordinarily heavy tails. So if, you know, one of the predictors happens to be strong, it's not shrunk towards 0 too much. But a lot of the ones that just have like tiny effects, they're going to get shrunk to something very near 0. And then if you do prod spread or something like that after that, it's likely going to find that, okay, here's a model with like 4 or 5 predictors whose expected long predicted density is just as good as the model you started with, which had tons of predictors. So we sort of saw an example of that on the homework as well. Another thing that actually is hierarchical model, but we didn't say it at the time, are these generalized linear models that have smooth but nonlinear effects. So we did that with like age or something like that at one point. Those are actually, you know, prior, you know, it expands out the coefficients with a bunch of basis functions and whatnot and puts normal priors on everything. Okay, what's the standard deviation of those normal priors? Treats that as unknown, and then has hierarchical prior on that standard deviation of these normal priors that sort of collectively comprise this smooth nonlinear function. And the you know, the bigger those posterior standard deviations on those or posterior distribution on those standard deviations are, the more wiggly the smooth but nonlinear function is, and the smaller those posterior standard deviations turn out to be, the more linear the function turns out to be. So those are another example of hierarchical priors. But even the bowling example was hierarchical. Now, it didn't have any parameters per se, and that's why we started with it. But it basically had a hierarchical likelihood where the you know, the distribution for the number of pins knocked down on the second roll depends on what happens on the first roll. So, you know, you could estimate that if you had data, but it had this sort of like, first the first roll happens, then the second roll happens. And if you just sort of extrapolate that thinking to priors, okay, we have priors like at this level, and those are conditional on other parameters, and those may be conditional on other parameters. It's basically just like stringing out, you know, with bowling you only have 2 rolls in a frame, but you know, some other process where it's just like step 1, step 2, step 3, step 4, and then, you know, step 4 is conditional on step 3 and all that other stuff. So hierarchical models are actually, you know, something that we've already indirectly dealt with. We'll deal with it more explicitly this week, and it's a very general idea of, okay, my prior for one parameter depends on, is conditioned on some other unknown that also has a prior, and who I'm going to estimate its posterior distribution along with everything else. So this is actually a very general idea. Unfortunately, if you like Google for hierarchical models or whatever, it's going to be overwhelmingly dominated by a discussion of hierarchical models from a frequentist perspective, which, you know, if you interpret it strictly, there's very narrow circumstances in which a hierarchical model would be applicable because they don't talk about, or they don't have priors. Once you know, take the Bayesian route to any of these models, there's going to be priors on the parameters. Indeed, there should be, you know, at least somewhat informative priors on the parameters a lot of times, and that opens up a lot of opportunities to have the prior for one thing depend on some other unknown that also has a prior, and you also get the posterior distribution out when you estimate it with Stan. And so a lot of the discussion is on kind of a very narrow case of hierarchical models from a frequentist perspective, rather than talking about it as a more general Bayesian idea which we're going to do this week. So why would you want to use a hierarchical model? So let's think about an example like this. You collect some data on people in New York, and you estimate the posterior distribution of some parameters with like stand GLM or whatever it may be. Okay, so now you have a posterior distribution of coefficients and like intercept and some other things. Okay, you decide for my next project, I'm going to collect data on people who live in Connecticut. So it would be totally appropriate for a Bayesian perspective to use the posterior distribution you obtained by conditioning on people who live in New York to inform your next prior distribution when you go to collect data to condition on from people who live in Connecticut. That's just using the posterior from one thing as a prior for the next. But it seems intuitive that, okay, well, the posterior distribution for conditional on people in New York should be relevant to the posterior distribution conditional on data from people in Connecticut. But there's no overwhelming reason to think that the data generating process is going to be exactly the same in Connecticut as it was in New York. Like, why would the coefficients on the variables that you collect be exactly the same in two states, particularly if we're talking about something where state laws and state regulations that may differ from one state to another are affecting the data generation process, like differences in tax law between New York and Connecticut, affecting the savings and the other life decisions and whatnot that people who live in those states might make. So it's totally reasonable to think that the data generating processes between two similar states would be similar. But it's probably on the unreasonable side to think that the data generating processes are exactly the same. So you wouldn't just take your posterior distribution literally from New York and apply it as your prior distribution for Connecticut. You would want to sort of add some variance to it to allow for the possibility, distinct possibility, that the coefficients and whatnot that govern the data generating process in Connecticut are not exactly the same as those in New York. So it might even be reasonable to say your prior expectation for the coefficients in Connecticut is the same as your posterior expectation that you got from the coefficients when you conditioned on data in New York. But you would want to add more variance when you go sort of extrapolate your model from one state like New York to another state like Connecticut, and especially if you want to extrapolate from a state like New York to a state like Mississippi, which is, different in a lot of respects. You would want to add a lot more variance to your posterior distribution that you obtained from New York if you were to go to use it as your prior for the data generating process in Mississippi. So it's just about sort of taking data generating processes that are similar to a greater or lesser degree and allowing, the posterior distributions that you get from one state to influence the ones from another state. Well, what if you get like all the data at the same time? Well, a hierarchical model sort of allows the posterior distribution from any one state. It's not going to be independent from the posterior distribution of the coefficients and whatnot in another state, even states that are very different, but you don't have to assume that the posterior distribution of the coefficients is exactly the same in any two states. Indeed, you can estimate the degree to which the data generating process differs from one state to the next. Estimate how much heterogeneity there is in the data generating process when you get all the data at the same time if you use a hierarchical model. And for that reason, in the reading for today, Richard, making his standard argument that hierarchical models should really be the default way that you approach data, and the sort of flat models that we've been to some extent talking about so far, where there's no heterogeneity in the data generating process across groups would be a fairly rare special case that you would have to justify based on the data, first by estimating a hierarchical model, and then finding in the posterior distribution, there's not really a whole lot of heterogeneity from this group, to that group, to another group. And therefore, going to a simpler model that constrains the data generating process to be the same across all groups is expected to have a better log predicted density or some other justification for saying, well, the heterogeneity in the data generating process is so minor that we might as well model it as if it doesn't exist. But that is, I think, I would anticipate a rare situation when doing quantitative methods in the social sciences, where heterogeneity is probably the rule rather than the exception, or we don't have much at all theoretical basis for dismissing the idea that the data generating process could have this heterogeneity in it outright. And I think that is particularly the case with data sets that are larger or include data from lots of different types of people and whatnot, and that when you sort of expand the reach of your data collection, you expose yourself to more and more opportunities for the data generation process to be a little bit different as you sort of extend the data set to more and more different types of people. And that gives you an opportunity to specify like a fairly rich hierarchical model that would allow you to capture and to estimate the degree of that heterogeneity. But that's not the route that a lot of people take, particularly with the supervised learning thing, where these hierarchical models are not really a thing because you can't just estimate them just with optimization, which is what the computer scientists and the engineers and whatever are programmed to do. So they'll take a data set like, Facebook sized thing and, basically estimate a fairly simple, lasso or whatever model, where, okay, they penalize the coefficients to the extent they're not zero, but not really allowing heterogeneity from one country to the next, and how users from that country interact with Facebook, and certainly not doing anything to try to capture the uncertainty as to what the parameters are or how much heterogeneity there is. But basically, when McElry says that, well, hierarchical models should be the default, hierarchical models are what Bayesian people almost always are doing anyway, and always wanted to do even when they didn't really have the technology to do that. He's implicitly saying, well, the Bayesian approach should be the default because in the Bayesian world, it's totally natural to allow for the possibility of this heterogeneity and try to estimate it. It's only unnatural if you try to approach one of these models from a frequentist perspective. And it's really unnatural as opposed to all the other things that are unnatural about the frequentist perspective. So one of the things that falls under the umbrella of hierarchical models, but no one frames it this way, are interaction terms. So let's suppose you have a model for like, does someone turn out to vote or whatever in an election, and you want to allow the coefficient on the person's age to be a function, a linear function, let's say, of the person's income. Does that model make sense? I don't know, maybe, but it's totally possible to do. Just like put an interaction term between age and income. But we can also represent that the same way, in an equivalent way, when drawing from the prior predictive distribution, using ideas that would be more typically associated with hierarchical models. So we're going to return a matrix of draws that's S by N. S simulations in people in the prior predictive values are either 0 or 1, failure or success. We have an integer S for the number of simulations we want to do, and we have a vector for the person's income and a vector for the person's age. So we just allocate the draws, and then we go loop from S is 1 up to the number of simulations. So we draw like the intercept alpha from some normal prior. We draw the slope on the income variable from normal prior with like standard deviation of 2. Obviously, you could change all of those. And then I want to draw another intercept and another slope, gamma 0 and gamma 1 respectively, for this piece here. So I'm saying this vector of parameters of size n gamma is equal to gamma 0, which is like an intercept, plus gamma 1, which is a slope, times the person's income. And I'm going to use gamma as the coefficient on the person's age. So I've specified how sensitive the person's log odds to voting is with respect to their age to depend in a linear way on what their income is. And so rather than having, you know, intercept plus slope times thing be a way of constructing like a linear predictor for data, now I'm using that intercept plus slope times, in this case, income, to be my specification for other coefficients, gamma in this case. And then I'm going to take gamma and element-wise multiply it by age to get the other part of the log odds for whether this person's going to vote. So the full specification for the log odds is alpha, the original intercept, beta, which is the coefficient on income for the log odds of voting, plus gamma, which was on the previous line, this linear thing, which is a function of income, element-wise multiplied by the person's age. In other words, the person's income is influencing their log odds of voting in 2 ways. Directly, so to speak, through the coefficient beta, and indirectly, so to speak, through the coefficient on the person's income, which is a linear function of income. Doesn't have to be linear, but just that's the way interaction models usually are. Now, if you do some algebra, you can see what's asserted in this comment is true, that the values of the n values of the log odds here are the same as if I had done alpha plus beta times income plus gamma 0 times age plus gamma 1 times the product of income and age, where the product of income and age is the more conventional way of specifying an interaction term. If you just rearrange things, you can see that the 2 ways there that I've given for constructing eta, the log odds, are exactly the same for all people. And when you go to estimate this with like GLM or whatever, it's using the second form. So you get back estimates of alpha plus beta and gamma 0 and gamma 1, where gamma 1 is the coefficient on the interaction term. And you get all that with the Bayesian approach as well. But if you want to, you could save the prior or the posterior distribution of gamma, which is the coefficient on the person's income. You make some analysis based on that. But either way you construct eta, it's equivalent, and then you can call Bernoulli-Logit RMG to get a realization from the prior predicted distribution. So this is a hierarchical model in the sense that the parameter gamma depends on other parameters, gamma 0 and gamma 1, which I have priors on, and which if I condition on data, I could get posterior distribution on. But it's equivalent, it has the same log odds, it has the same likelihood function as what you see all the time with just somebody does a model of voting and they stick in an interaction between the person's income and the person's age. It's the same log odds, and so it's the same likelihood. So questions about that connection between what you should be familiar with, interaction terms, and what you're probably more familiar with than what you realize already, which is hierarchical models, allowing one parameter to depend on another parameter in an explicit form. in this case linear. Didn't have to be linear. Does need to be explicit. Questions? So, let's do another example. This is a little bit more prone to someone referring it to a hierarchical model. Indeed, it was in the article that we were using as a basis for that homework problem on the previous homework, the one about police shootings from one county to the next and across the different races, depending on whether the person was armed or unarmed or whatever. So this is drawing from the prior distribution of relative risk, like we did on the homework, but this is actually going to correspond to what was done in the paper. So I pass in integer s, the number of prior simulations I want to do, integer n, which is the number of counties. I just allocate my matrix to hold the results, which are going to be real numbers, this ratio of relative risk for being shot unarmed if you're black versus if you're white. And then I make a vector of zeros, which you'll see how it's used in a second. Not sure if we've talked about this function, rep underscore vector. It's very similar to rep in R. You can just sort of create a vector that has all the same elements, in this case 0, and the vector is going to be of size 6, because we have in the original paper 6 combinations of race and weapon status. So the way in which they order it in the paper is black unarmed, black armed, Hispanic unarmed, Hispanic armed, white unarmed, white armed. So those are the 6 things that we want to be drawing intercepts for at the county level. So I loop from 1 to the number of simulations, allocating but not yet filling vectors for mu and sigma, and this L, which turns out to be a Cholesky factor, which we'll talk about that in a second. So then we draw a 6 by 6 correlation matrix row, which is supposed to capture the correlation among the 6 intercepts, or the 6 intercepts for each of the one corresponding to the different races and the different arms. So we're going to draw that from an LKJ distribution, which we talked about at the end of class on Thursday. It's this prior over correlation matrices, and if you set that exponent eta in the LKJ prior to 1, then it was 1 minus 1 in the exponent. And so it was something raised to the power 0, so that's a constant. And so this is what the paper assumed, okay, uniform distribution over the 6 by 6 correlation matrices, which is this convex set, because correlations, one, they're bounded, but also they have to satisfy the positive definiteness constraint. And so subject to that constraint saying, okay, all 6 by 6 valid correlation matrices are equally possible before I start seeing the data. Okay, then we're going to loop from 1 to 6 and fill in mu and sigma. So those mu's were taken from normal negative 14.4, and the sigmas were half Cauchy with a scale parameter of 5. So we fill in those for the 6 different types of people, and then L gets filled as these standard deviations, which we just got, times the Cholesky factor of our correlation matrix. So a Cholesky factor, again, is going to be a lower triangular matrix. If you pre-multiply a lower triangular matrix by a diagonal matrix of standard deviations, the result is still going to be a triangular matrix. It's now just the Cholesky factor for a covariance matrix rather than a Cholesky factor for a correlation matrix. So by scaling a Cholesky factor for a correlation matrix from the left by a diagonal matrix of standard deviations, you obtain the Cholesky factor for the covariance matrix, which, as I alluded to on Thursday, makes things easier when specifying these multivariate normal priors to do that in terms of the Cholesky factor rather than in terms of a covariance matrix or a correlation matrix. But if you needed to or wanted to, you could obtain the covariance matrix just by taking the Cholesky factor and multiplying it by its own transpose. So L times L transpose equal sigma. So then we loop over the number of counties. So I should say that like everything above the loop from 1 to n is basically the parameters at the United States level as a whole, like the overall, you know, mu and sigma or whatever. Then we drop into the loop from the first county to the last county, and the parameters underneath here are county specific. And so basically we're saying each county has this multivariate normal deviation from the country level parameters as a whole. And that's why we get the heterogeneity or possible heterogeneity in the data generating process for shootings across counties. Where, okay, so there's multivariate normal deviation from these 3,000 counties relative to the United States as a whole. But, you know, some of those counties are going to be in the extreme left or whatever. It's hard to say left in 6 dimensions, but the extreme, like, bad tail of the multivariate normal distribution. And in those, you know, counties, we may very well see relative risk ratios that are much, much worse than for the country, you know, as an average on the whole, and much, much, much worse than like the best counties where, you know, the police are getting good training and stuff like that. Anyway, we drop into the loop from the first county to the last county. We draw theta, the 6 intercepts, 1 for each type of person, from a multivariate normal distribution using the Cholesky parameterization. So it's basically taking realizations from independent from a standard normal, multiplying them by L, and then we shift it over by mu. But you can use the multinormal Cholesky RNG function to sort of handle the internal details about that. Okay, for this county, we now have 6 intercepts. So the paper did that weird like 6 binomials thing, but it would have made sense to do 2 trinomials instead of 6 binomials. So that's what we'll do there. We get the 2 intercepts and a 0 for the white unarmed and armed, and then we get the 2 intercepts and a 0 for black unarmed and armed. We do a log softmax transformation. So on the homework, I guess we were doing softmax, but that could lead to some numerical instability where both the numerator and the denominator underflow to 0, and you get like 0 over 0, it's NA. So a better way to do it slightly is to take the log softmax, which is numerically stable, subtract the first element of the log softmax for blacks. This is corresponding to black unarmed. From the white unarmed one, take the difference between those 2 things on the log scale, anti-log it to get a relative risk, and stick that into the sth row and column, loop over all the counties, do that S times, and now you have a matrix of prior draws of the relative risk. Again, it's going to have a median of 1, but potentially a very heavy tail. So allowing for the possibility that some counties may be much more likely to shoot someone unarmed if they're black than if they're white. So that basically, except for changing the weird 6 binomials into 3 multinomials thing, is like what that paper was doing when it talked about in the appendix that stuff about like multinormal Cholesky and all that. Now, last week we were still learning the matrix algebra stuff, so you know we kind of simplified this down, maybe in a slightly artificial way, but maybe in a justifiable way to just make it so we could use bivariate normal. But what the paper actually did, for better or for worse, was the 6-dimensional multivariate normal prior on the intercepts for the 6 different types of people that they had data for people being shot on. So that's pretty much all that paper had, or that's the model, more or less for that paper. And it's, you know, just a multi-level model where the prior on each county depends on the mu's and the sigmas and the correlations at the country level. So we have these sort of two levels. Some people, specifically in situations like this, refer to hierarchical models as multi-level models. So we have the country level where mu and sigma and the correlation matrix live at. And then in each county, our prior is, well, okay, that county is only going to differ in like a multivariate normal way from the country as a whole. And, you know, among 3,000 counties, some are going to differ a lot in one way and some are going to differ a lot in another way. Most are going to be pretty close to the national average, but that's just, you know, a way of thinking about these multi-level or hierarchical priors when there's a very natural grouping to the data. Now, counties are not really a very natural phenomenon, but that's sort of the level, the most disaggregated level that they could get reasonable data on, you know, shootings. But for other things, you know, you can get census data down to like the census tract, which is like a few thousand people. And so, you know, in that data, if it comes from the census, you know, is usually pretty reliable on all the demographic factors of the couple thousand or whatever people who live in that, you know, tract, which just, you know, doesn't exactly correspond with the zip code, but it's a similarly sized, small, you know, thing. And so you could do, you know, hierarchical models where the parameters differ from one census tract to the next, but they're sort of linked in a hierarchical structure of, you know, having commonality within states, and the states have some degree of commonality with some degree of heterogeneity across states. And so you can do these multi-level models, you can stack them up like a cake, and basically say, okay, here's the country level, here's the state level, here's the county level, here's the census tract level. And it's just this sort of 4-level pyramid of priors, each one as you get more disaggregated, depending on the parameters at the slightly more aggregated level. Indeed, the most canonical examples of these sorts of models come from the educational testing, educational research world, where it would be like totally commonplace to have, okay, priors at the national level for like how they influence, you know, how well the students and whatnot do on tests. And then, you know, there's deviation from each state relative to the national level. And then within each state, there's deviation in each school district. If we're talking about public schools, there's certainly going to be deviation if we talk about, you know, public schools versus private schools. But let's just say we only have data on public schools. So within each state, there's, you know, variation from school district to school district. Within each school district, there's variation from school to school. Within each school, there's variation from student to student. Within each student, there's variation from, you know, test to test. You know, kids these days, they're taking standardized tests like every week. And, you know, there's variation in how well they do, you know, from one week to the next. So, you know, we had different amounts of heterogeneity going on at all levels of the model: national, state, school district, school, and then student over time. That's another example of specifying one of these structures. So questions about this, or the idea of, you know, hierarchical models letting things at a more disaggregated level, your priors for those depend on the parameters at the next level up. In this case, with the police shootings, we just have 2 levels, really, counties and national, but in other situations, we could do other sorts of divisions of things into groups. Okay, so one little piece of math before we can move on, which is Kronecker products. It was talked a little bit about in the reading, but this is another way besides like scalar product and besides matrix product to think about multiplication from a linear algebra way. So the Kronecker product is indicated by an X in a circle with it. It's defined for any two matrices. They can have whatever sizes. And it's defined as a matrix. So if A has m rows and n columns, and B has p rows and q columns, the resulting matrix is going to have mp rows and nq columns. So you take the rows of the two matrices, multiply them together. That's the rows of the resulting matrix, and then do the same thing for the columns. So this Kronecker product is going to create a bigger matrix than either of the two constituent matrices that you're Kronecker producting together. And the Kronecker product is basically defined as you take each scalar in the matrix on the left, A, and you multiply it by the whole matrix on the right, B. And then you stick that block of basically B scaled up by some coefficient of A into the appropriate place in the resulting matrix. So in the top left, we have A11 times the whole matrix B, and then adjacent to it on the right, we have A12 times the whole matrix B again. Below the first block, we had A211 times the whole matrix B, and etc. So we fill in like all the blocks of the resulting matrix, creating a much bigger matrix. Or you can think of it as like having a bunch of matrices within a matrix, and each of the sub-matrices are like a scalar times B. And the scalars, each of them come from the elements of A. Now, often when you see these Kronecker products in the hierarchical modeling context, either A or B will be some sort of simple matrix, like an identity matrix. So if A is the identity matrix and B is like, you know, sigma or some covariance matrix, something like that, then, you know, everywhere where A is 0, you're just going to get 0 times sigma, which is 0. So most of these blocks are just 0, but down the diagonal, you have sigma, 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 sigma when you Kronecker product sigma with I. I being on the left, sigma being on the right. So that's the definition of a Kronecker product. And you'll see these things used in a lot of different situations, inclusive of hierarchical models, which we're going to try to like restate in a general form now. So if we have some vector of coefficients, let's say at the country level, beta, but just to be neutral about these, I'll call them common coefficients. That is, they pertain to like all of the units in the data set. And then we have these other things, a vector B, but B is subscripted by J. So J, capital J is the number of groups that we have in our data set. And so the B sub J parameters are the deviations from the common coefficients by group J, which could be like Manhattan County or, you know, XYZ school district, whatever. So deviation from the next level up, the common coefficients. And then if we stick all those group level deviations B together, concatenate them together to make a big long vector, then we can write the model in basically two ways, a hierarchical model in two ways. One which lends itself to Bayesian estimation, and one which lends itself to frequentist estimation. And as is usual, these things are much more different than perhaps they appear. So if we just think about this continuous outcome, normal errors, whatever, it applies even in other forms of GLMs. From a Bayesian perspective, the conditional mean, what we expect the outcome to be for a particular observation, is X, whatever predictors, times the common coefficients, plus Z times the deviation in the common coefficients that's applicable to this group. So Z is a matrix has the same number of rows as it has observations, it tends to have a lot of columns because it represents the interaction between X, or at least some columns of X, and the group level indicators. So if Z, in like the case of police shootings, Z might have 3,000 columns, you know, one or 3,000 times 6 columns, something like that, one for each way that the county could deviate from sort of the national norm on these intercepts things. So in that, there was no real coefficients. It was just like a bunch of intercepts, but the same sort of thing applies. Anyway, so from a Bayesian perspective, the conditional expectation of this outcome is given the observations X and the observations Z. So it's the sum of, you know, the common coefficients beta times whatever the predictor values are on their X's, plus the deviation from those common coefficients represented by, you know, some columns of Z being multiplied by the corresponding elements of B. And so we have a conditional expectation given X and Z, or at least we do if we're thinking about this from a Bayesian perspective. If we were to think about this from a frequentist perspective, they consider the conditional mean to just be X times beta. So not conditional on Z, just conditional on X. And you might say, okay, well, what happens to Z? Well, from a frequentist perspective, Z times B is part of the error term. Whereas from a Bayesian perspective, Z times B is part of the conditional expectation, and the error term is just epsilon. But from the frequentist perspective, the error term consists of epsilon, which is like independent across counties, plus Z times B, and Z times B is what induces dependence in the error terms across counties. And B can in turn be decomposed in this form, where we have a Kronecker product between the identity matrix and the Cholesky factor of the covariance matrix times U, which we'll see gets these independent standard normal assumptions associated with them. And so that is the same, you know, what gets multiplied by what in the Bayesian specification of these multi-level models as it is in the frequentist specification of these multi-level models. But what is part of the conditional expectation and what is part of the error term differs between the way the Bayesian hierarchical models are implemented versus the way frequentist hierarchical models are implemented. And consequently, from a Bayesian perspective, conditional on X and Z, we're assuming the counties or whatever are conditionally independent. Whereas from a frequentist perspective, conditional on X only, the common predictors and the common coefficients, the counties are not conditionally independent because this Z times B business is correlated across counties. And so they're thinking about this normal model as having correlated errors, whereas for Bayesians, we're thinking about it conditional on X and Z, and that gets rid of the correlation across counties, or at least that's the assumption. And the same sort of thing holds with GLMs if you have some inverse link function that you're applying to eta to obtain the conditional mean. Again, we have the question as to, you know, is Z times B part of the error term, or is it part of the signal? And so we'll come back to this, but maybe it makes a little bit more sense to just go on the next slide and try to explain what the frequentist perspective on these models is, but it's weird. And it's weird because frequentists are also making an assumption that U is distributed independent standard normal across counties or whatever the groups are, independent multivariate standard normal. And that implies that the B's, the deviation from the common coefficients in the jth group, is going to be multivariate normal with covariance matrix L times L transpose scaled up by sigma squared, which is just the variance of the errors, the epsilons. And so that's a multivariate normal. And you say, wait a minute, why are the frequentists putting priors on things? Well, what frequentists are doing is they're going to integrate all the u's and implicitly all the v's out of the original likelihood function to obtain a new likelihood function called the integrated likelihood function that only depends on the betas, sigma, and L. And then they're going to choose estimates for beta, sigma, and L to maximize the integrated likelihood. So these distributional assumptions they're making on the U's are not priors, because frequentists don't consider those to be parameters. They consider those to be part of the error term. And in order to get a likelihood function that's a minimal to maximization, they need to integrate those out of the original likelihood function, which, if everything is Gaussian, can be done analytically in this like one case. And it leaves an integrated likelihood function that's multivariate normal that has expectation x times beta, and whose variance covariance matrix, which is n times n, is this expression here involving z and L times L transpose and all that. So they're maximizing or choosing beta and sigma and L to maximize a multivariate normal likelihood. Whereas when we do it in the Bayesian case, conditional on x and z, we have sort of independent contributions to the overall likelihood. But that still doesn't really explain why frequentists are putting these normal assumptions on these sorts of things. And the reason why that is, and it overlaps with another thing which causes a lot of confusion, is the frequentist tendency to refer to the estimates of beta and whatnot as fixed effects, or estimates thereof, because they're thinking of beta, sigma, L, etc. as being fixed across repeated samplings of data from this population. So if we do the schools thing, one way of collecting, just sort of a simplified example, one way that's typical of collecting data is to use cluster sampling. So like the Department of Education, when they want to do a study or something like that, they'll set up a design where they say, okay, first we're going to randomly select 100 schools from like public schools in the United States as a whole. Okay, we do that. And then within each of those 100 schools, we're going to randomly select 20 students and like give them more tests or whatever. And then, use that and then analyze the data or whatever. So it's collected in two stages. First, there's a random sampling of schools from like the population of schools. And then within school, there's a random sampling of students from that school. And that's a much cheaper way to get data than doing simple random sampling from students as a whole. And it has a lot less variance, and you can make corrections and whatnot. So you hardly ever see anybody doing simple random sampling from a large population because it's totally impractical and has a huge amount of variance. More likely to see cluster random sampling or stratified random sampling or other sorts of schemes like this where there's multiple levels of data collection and multiple levels of randomization. And so frequentists are thinking of these common parameters, which they call fixed effects, beta and sigma and L and things like that, as for the country as a whole. Whereas all these deviations from one school to the next are just error. And in particular, these deviations, the B's or the U's, depending on how you parameterize it, from one school to the next, are not fixed effects, they're random effects, because if we were to repeat the design again, we would get a different collection of 100 schools than the 100 schools we got the first time we ran the data collection process. And so if like the first time that elementary school over here on 120th got selected, the next time we did it, most likely that elementary school is not going to get randomly sampled again. And so we only get observations from that elementary school once. The next time we do it, we get like a totally different set of schools. And so the intercept and the coefficient, whatever, for that school on Amsterdam and like 122nd, we don't get repeated information on it. We just get information on it once. And so because the school-specific deviations differ from one school to the next, and what schools get included in the first stage of the sampling differs, when we do this, hypothetically over and over again, those are changing. Those are not fixed. Those are random. They depend on the random realization of what schools are selected to collect data on. And so they aren't even parameters, because parameters in the frequentist world are constants. And consequently, if they're not parameters, you can't estimate them. So they're just part of the error term. Yeah, they're governed by sigma and L or whatever, but they're really just variance components. And so by saying, okay, this is a model that's appropriate for cluster sampling designs, they're distinguishing between what is permanent, the sorts of things that would be the same if they were to do the data generating process, sample from it in the two-stage way over and over again, versus things that would be changing every time you change the first stage. And as usual, even though it's weird, the only thing that frequentists apply probability to are the distribution of an estimator across randomly sampled data sets from the same population if you were to do this thing over and over and over again, both stages of a cluster random sampling design. And so if you were to do this over and over and over again, you get a distribution of estimates for beta, because that collection of coefficients is the same each time you do the first stage. But you never get the same school twice when you do this over and over again, so you don't really even have the ability to estimate the V's. So they're not parameters, you're not estimating them, they don't have a sampling distribution across data sets. They're basically nuisance parameters or random effects that you just need to take into account of, because they make the errors correlated across schools. And if you assume the errors were independent, then you would be getting like the wrong standard errors and p-values and confidence intervals and whatnot for your estimates of the betas. But this assumes that what you're really interested in are the population parameters, the betas, the sigma, the L, whatever, and you don't care about the school-specific deviation. And maybe if you're like the Department of Education or like, some researcher who sends their kids to private school anyway, maybe you don't care about the school-specific deviation. But the parents of the kids who send their kids to elementary school on 123rd in Amsterdam, they care about that school's deviation from the normal, or from the country as a whole, or from the city as a whole. And is it in like the good direction or the bad direction? So somebody may care very much about what these deviations are, and those somebodies need to be using Bayesian estimation techniques, because those are the only ones that are actually estimating the posterior distribution of these school-specific, county-specific, whatever deviations, conditional on the data we've actually collected, as opposed to, what's the conditional distribution of the estimators of the betas across two-stage cluster sampling random sampling designs. If we were to do it over and over again, but by the way, we're only going to do it once. And so that's why this distinction between what's part of mu, conditional on X or conditional on X and Z, and what's part of the error term, drives this sort of difference in perspective on multi-level models between Bayesians and frequentists. And why, when you see this talked about from a frequentist perspective, it's sort of somewhat narrowly justified to things like cluster sampling designs, where in Bayesian it's a much more general thing, where we could have parameters that pertain to this school or this county, these types of people, deviating from the typical school county person in some sort of prior that we specify condition. So questions about this? Of course, we're going to estimate this from a Bayesian perspective, in which case it's really just like, a generalized linear model, except in addition to these priors on the betas, we're also going to have priors on the B. And the B is multivariate normal. So we can reparameterize that so it's standard normal in the use, and then multiply it by HLSP factor, whatever, and it's distributed multivariate normal. But basically, it's just a generalized linear model with more coefficients. And like one batch of the coefficients beta, we have this multivariate normal prior on. Or one batch of the coefficients B, we have this multivariate normal prior on. And you can put whatever prior you want on the betas and sigma. And usually you would do the LKJ thing with L, but your other choices there. Indeed, you don't have to limit yourselves to multivariate normal. You can do multivariate T or other sorts of distributions. It's just you see multivariate normal, it's 99% of the time, because usually you're seeing this from a frequentist perspective, and the multivariate normal distribution is the only one that lends itself to analytically integrating the B's out of the likelihood, so you get a new likelihood function that doesn't have the B's in it anymore. Any other choice for the distributions means you have to do the integrals numerically, and that's not going to work in high dimensions. But anyway, for better or for worse, and by that I mean for worse, the sort of discussion of these hierarchical models tends to be dominated by papers and software that are looking at this from a frequentist perspective, and we're talking about the LME4 package, which is very similar to estimators in Stata and SAS and things like that, but it introduces its own formula syntax for specifying these multi-level models, which we use in our StanArm, even though we don't use like the same vocabulary of random effects and fixed effects, stuff like that. So if you specify, one of these parentheses, like one vertical bar G things in the formula of one of these multi-level models, that's saying allow the intercept to vary in a normal fashion from one level of G to the next. So G is going to be a factor that has different levels. So G could be your county level, or your county indicator, or your school indicator, whatever it may be, saying, okay, allow the intercepts to differ from one county to the next, according to what, from a Bayesian perspective, would be a normal prior, or from a frequentist perspective, saying there's like normal error from one county to the next in these intercepts. If you do something like this, x plus parentheses x vertical bar G, that is saying, okay, allow both the intercept and the slope to vary from one grouping level to the next, one county to the next. So there'd be like county-specific intercept and county-specific intercept deviation and county-specific slope deviation from the national intercept and the national slope, respectively. If you put two vertical bars, that means, okay, there's county or group level deviation in the intercepts and county level deviation in the slopes, but the county level deviations in the intercept is independent of the county level deviations in the slopes. Whereas if you just put like the one vertical bar, then you're saying, okay, there's an unknown correlation between the deviation in the county level intercepts and the deviation in the county level slopes within each county that we also need to estimate, and that's another parameter at the national level. There's other things too in terms of like nesting, different ones. I think there's some more possibilities. If you click on the FAQ, I think that one is pretty comprehensive, and it has a lot of other details and stuff, and warnings and things like that that you might have to worry about if you were to do this from a frequentist perspective. But in addition to sort of the weirdness about, okay, this only applies to cluster sampling designs. You also, when you get into multi-level models, start to see the limitations if you adopt optimization as your way of doing estimation. And so for the things that we've done before, that wasn't such a sharp contrast, because if you did like maximum likelihood estimates, those tended to be not too different from the posterior medians that we were getting when we used like STAN and MCMC. But when you start doing multi-level models and you do optimization, you're more likely to see optimums on the edge of the parameter space, like where some of the diagonal elements of L are 0, or sigma is 0, or something like that. And that is a disaster from a frequentist perspective, in the sense that their estimators assume the optimum is interior to the parameter space as opposed to on the edge of the parameter space. But it's a consequence of saying, I just want the mode, as opposed to saying, I want the whole distribution. Because the mode may very well be on the edge of the parameter space, where like something is 0 or whatever. But the rest of the distribution is not on the edge, it's to the interior. So the mode, the median, the tails, all that, that's interior to the parameter space. And you might very well want to know that, or indeed if you're taking a Bayesian approach and you want to like maximize your expectation of utility, you need to know all that. It's just, what we've done so far, like the mode tends to be in the center, like in the interior. And so there's not as much cost to just sort of like basing the whole thing off the mode. But when you start doing multi-level models, that breaks down, and the mode is often in a weird place and has no real correspondence to like the posterior mean or the posterior median. And so you have to do a genuinely Bayesian MCMC approach in order to figure out where posterior means and medians and whatnot are. So an example of that comes from a paper. It was in a psychology journal that Jonah did with some people he met on the internet. Whatever, you can download the data. It's one of these psychology studies where they like poke people or something like that and then ask them a bunch of questions and see how, and like hook their brains up to things and see how salient the questions that they're asking are, depending on these experimental conditions as to how agitated they make people beforehand. And so this is an example of estimating one of these models using the same syntax as in the LME4 package, but doing it with Bayesian estimation rather than frequentist optimization estimation. So we're saying allow the intercept and the coefficient on the arousal variable, which is experimentally manipulated, to vary from one person to the next. So this PID factor variable that's on the right side of the vertical bar is the person ID. So they do each person, they subject to a bunch of these tests. And so allow the intercept and the sensitivity to vary from one person to the next in a bivariate normal fashion, and then estimate a common intercept and coefficient on the thing that they're manipulating. Normal priors on the coefficients, normal prior, but autoscale equal false in this case for the intercept. You get back posterior median, posterior standard deviation of the common intercept and the common slope. Now, what it says over here, error terms, that's like frequentist language, but we wanted to adopt the language of LME4 to make as smooth a transition as possible for people who use that package and run into various problems that can come up with it. And so over on the right is basically saying, okay, we got a posterior mean correlation of negative 0.64 between the person level intercept and the person level slope, as far as their deviation from the average, and posterior means of the standard deviations on that from one person to the next. And so this estimated, there were 20 people in this experiment. So each person has 20 parameters, or 20 intercepts and 20 slopes, so 40 parameters total. And then there's an overall intercept and slope, so that would be 42. And then a few more, I guess 3 more for the unique components of a bivariate normal prior on those, and then 1 for the standard deviation of the errors. So I think 46 parameters in total. So you might ask yourself, okay, we did that, it seemed pretty easy, but what were the priors? So if you call prior summary, it will tell you a little bit about that. All of this should be familiar, except for the covariance part, which I'll explain next, which is, the prior on this bivariate normal deviation from one person to the next from people as a whole in this multi-level model. So decov is short for decomposition of covariance. By default, all the arguments to that are just all 1. The first is the regularization parameter in the LKJ prior on this 2x2, in this case, correlation matrix, but it doesn't have to be 2x2. Conch is for the concentration parameter on the Dirichlet prior on the variance components. So again, those are going to be non-negative and sum to 1. And then I'm going to scale those up like we did last week by something that has a gamma prior, and that gamma prior has a shape and scale. And so the combination of that multiplied by the variance components gives you the, in this case, 2 variances, 1 for the person level intercepts, 1 for the person level slopes, but they can be correlated, and indeed the posterior correlation in those 2 things was quite negative in this case. So usually you don't have to change the default and it works really well in RStanArm. Some accessor functions, again, that we borrowed from like the LME4 workflow, fixf, which just returns the posterior medians of the overall intercept and the overall coefficient. RANF for random effects, even though we don't say that from a Bayesian perspective, returns a list, 1 for each grouping factor you include, but in this case there was only 1 grouping factor, the person ID, and so that's going to return back a list of like 20 because there was 20 different people, and then 2 columns that has their deviation from the overall intercept and slope respectively. And then if you call coef, it's the same way, but it takes like the person level deviations, adds them to the overall intercept and slope, and as a consequence you get like 66 and 0.38 here. So combining the overall intercept with the person specific deviation in the intercept and the overall slope with the person specific deviation in the slope to get sort of the overall sensitivity to the experimental treatment in this case. And like I said, the overall dimension to this posterior distribution is 46 because we have 2 parameters each for each person and then like 6 more. So we can do the same sort of stuff that we've learned to do with like flat models. Here we can call Lu. We could compare this against other models, simpler models, more complicated models. But I want to draw your attention to this estimate of the effective number of parameters, which is just 30.7, estimated reasonably precisely. But we just got through saying that this posterior distribution has 46 parameters in it. Why is my effective number of parameters, only less than 3/4 of that, maybe 2/3 of that? And that's because of the prior information. We're saying, okay, these person level intercepts and person level slopes, yeah, they're different parameters, but we have reasonably informative prior information that they don't differ that much from people as a whole. So your intercept and your slope don't differ that much from anybody else's intercept and slope. They differ in a normal fashion, but we're estimating the variance and the correlation of how they differ. And it turns out, the variance is not too big. The correlation is kind of negative. And so we have a lot of information that's sort of coming from the top level of the model into the individual levels. And that information is what makes the effective number of parameters we're estimating less, indeed much less, than the nominal number of parameters. So you see, frequent is like counting up degrees of freedom and stuff like that. all the time. It's really irrelevant what the nominal number of parameters are from a Bayesian perspective, because you can specify arbitrarily strong amount of prior information on any of those parameters. What matters is the effective number of parameters being estimated and whether that is reasonable in light of the 272 observations that you have. Is pushing it, but maybe. Anyway, so you can do the regular loop stuff. You can do the regular posterior predictive checks, but you also have the opportunity to group your posterior predictive checks by the grouping variable that you put in the model, in this case, person ID. So we get, the usual thing with like ribbons indicating the 50% and the 90% interval as X, which is the experimental variable, varies. And we can see from the dark blue lines in the actual data, this is a pretty noisy, weird, wiggly relationship. Tends to be increasing for like most people, but it just has a whole lot of seemingly implausible variation in it, where it just zigzags up and down, for a little way on, for the most part, an upward trending thing. And that's really what multi-level models get you. Instead of having your coefficient and intercept for person number 7 being completely influenced by whatever that blue line for person number 7 is, we're taking into account that person number 7 is not that different from person number 8 or number 6 or number anybody else. And so by allowing the results for 8 and 6 to also influence the estimates we're getting on 7, we get regularization. And so overall, these blue estimates and whatever we're getting from the model are like trending up. We have uncertainty about it. We have uncertainty that's specific to particular individuals, but we're sort of abstracting over all like this weirdness in the actual data that is probably just noise. And by doing so, we get a model that is less prone to overfitting the particular 20 individuals that we got in our experiment, and better equipped to predict future data on like different people or even the same people better than we would if we didn't do any of this regularization, partial pooling in the slopes and intercepts across people. So we're out of time for today. We'll pick it up for tomorrow, do the reading, but we'll sort of go through what BRMS can do with these hierarchical models, which is actually very similar, but because it's compiling the models at runtime, it has a lot more flexibility to do a lot more different types of models, but again, with these hierarchical priors. So see everybody on Thursday.